Hi, today we're presenting our work on CompOFA, Compound Once for All Networks for faster multi-platform deployment. Traditionally, model development has focused on designing, training, and deploying a single neural network. We attain one model with a fixed accuracy and a fixed latency. But CNNs have a characteristic accuracy-latency trade-off. The most efficient CNNs form a Pareto frontier where an increase in accuracy comes at the cost of increased latency. These latencies can vary widely across different deployment targets, depending on hardware capabilities, use case requirements, workload, etc. And so, for real deployment, it has become imperative to design and train models tailored to each deployment's latency constraints. But repeating these tasks for each deployment target is not feasible. Every deployment costs training time, compute dollars, ML and systems expertise, CO2 emissions, etc. Previously, Once for All, or OFA, proposed a technique to simultaneously train billions and billions of models in a constant training time. After this one time training, models can be independently extracted for any deployment. This cut down the training cost by orders of magnitude, but it remained expensive and inefficient. In OFA, we tackle these challenges via insights from CNN architecture design and practical systems deployment to create a smaller search space. CompOFA achieves half the training cost and 200 times faster search, all while building an equally accurate and diverse model family. In Once for All, there was a search space of subnetworks of a teacher model with varying dimensions like depth, width, etc. These model dimensions are sampled independent of each other, allowing all combinations of depth and width, as shown in the grid here. This choice was repeated at each block, leading to a combinatorial explosion of 10 to the power 19 models. Obviously, such a large search space leads to complications in training and searching. Stabilizing the simultaneous optimization of so many models requires a slow, phased training approach. Then, during model extraction, OFA depends on predictors for accuracy and latency since they can't be directly enumerated. We argue that this large search space is not necessary. Many of these models have suboptimal configurations and lie well below the optimal Pareto frontier. The latency differences between these models are also of too fine a granularity to matter for practical deployment. In this work, we look to insights to capture just these efficient models in a much smaller search space.
We start by looking into OFA search space and notice a specific trend that accuracy and latency of the models increase consistently with the growth of depth and width dimensions together. Therefore, we propose that even with a simple heuristic of growing both depth and width together, one can capture models with better accuracy and latency trade-offs. This observation is backed by prior work like EfficientNet and RegNet, which showed that model dimensions are not orthogonal. Thus, we leverage these insights to build a new design space called Compound OFA or CompOFA. By removing the suboptimal configurations, we reduce our search space to just 243 efficient models. These can be trained faster without progressive shrinking. We will now show the host of benefits provided from this smaller search space. On carrying out model extraction through neural architecture search, or NAS, we observe that CompOFA variants consistently match OFA on ImageNet accuracy across diverse hardware and latency targets. Due to the constrained search space, CompOFA achieves a new state of the art by obtaining a reduction in train time by 2x and a speed up in NAS by 216x without loss of Pareto optimality. Moreover, CompOFA also yields a better overall average accuracy than OFA. In other words, CompOFA has a higher concentration of accurate models at a population level. The source of our training speedup is indeed the smaller search space, which reduces the interference between the models and thereby removing the need for a phased training approach, which had slowed down OFA previously. And finally, we were also able to generalize CompOFA's heuristic across other architectures, namely MobileNet v3 and proxy-less NAS. In both cases, we see similar gains. Therefore, to conclude, CompOFA uses insights from CNN design and system development to improve the cost and usability of one-shot NAS with hardware constraints. To know more about our work, do check out the linked paper and the code repository. Thank you.